Today we're going to continue our discussion of probability by talking about complements and conditional probability and touching on Bayes' theorem. So we're first going to extend our multiplication rule to include the probability among several trials, which is going to let us find the probability that we get at least one of some specified event among several trials. And we'll also be looking at conditional probability a little bit, which we actually have had a little bit of an introduction to with the multiplication rule. And finally, we're going to look a little bit at what's going on with Bayes' theorem. So with complements, remember the complement is the opposite of the event. So if we have an event A, its complement is that A does not occur. So when we're talking about having at least one of something, what we mean is one or more. So the complement of that is not one or more, which means that there are no occurrences of that event. Because the complement is no occurrences and the event itself is one or more, so it could be 1, 2, 3, etc., finding the probability of the complement can be easier than finding the probability of the event itself. So if we want to find the probability of at least one, we're going to go through a series of steps. The first one is A is going to be the event of getting at least one of some event. And then A complement will be getting none of that event. So then we'll find the probability of A complement, so the probability that A does not occur. And then that'll give us the probability that none of that event occur. So if we subtract that result from 1, we take 1 minus the probability that it does not occur, that's going to give us the probability of at least 1. So let's take a look at an example. A study by SquareTrade found that 6% of damaged iPads were damaged by bags or backpacks. So if we have 20 damaged iPads that are randomly selected, we want to find the probability of getting at least one that was damaged in a bag or backpack. Well, at least one here translates to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, or 20 of them being damaged in bags and backpacks. And it took me a little while to list off all of those numbers, and finding all of those probabilities would also take a while. So instead, what we're going to do is consider the complement that what's the probability that none of those 20 iPads were damaged by a bag or backpack. So our complement is none, so we're going to get 20 iPads that were not damaged in a bag or backpack. So to find the probability that all of the 20 iPads were damaged in some other way, not by a bag or backpack, we're going to be multiplying the probability that one iPad was not damaged in a bag or backpack, which is 1 minus 0.06 or 0.94, times itself 20 times, giving us the probability for each of those 20 iPads all multiplied together. So we'll have 0.94 raised to the 20th power, or multiplied by itself 20 times, and that gives us a probability of 0.29. So now if we want the probability that at least one of the iPads was damaged in a bag or backpack, then we need to take 1 minus this probability of A complement that we found. So we'll take 1 minus 0.29, and we'll find a probability of 0.71. So now that we have our probability, we want to interpret it. So for a group of 20 damaged iPads, there's a 0.71 probability of getting at least one iPad damaged in a bag or backpack. Now 0.71 is not super close to 1, but it's also a decent way away from 0.5. So we wouldn't say that the probability is very high, but we would say that we can be reasonably sure because it is reasonably high. So we'll say that we're reasonably sure of getting at least one iPad damaged in a bag or backpack when we look at 20 damaged iPads. Right. So conditional probability, on to our second thing that we're going to talk about today. A conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. Now we saw this with the multiplication rule, where we needed to find the probability of B taking into account that A had already occurred. It's conditional probability. And the notation should look familiar from our multiplication rule. We use the probability of B with that vertical line and A, saying the probability that event B is occurring given that event A has already occurred. So our intuitive approach to finding this is going to be looking at the number of times that B occurs given that A has already occurred. So we're going to assume A has occurred, and then we're going to calculate the probability that B will now also occur. So if we formalize that, what we're doing is taking the probability of A and B, and we're dividing by the probability of A. So let's take a look at an example and find some conditional probability. So here we have a table, and we want to find if one of the 555 test subjects is randomly selected, we're going to find the probability that the subject had a positive test result, given that the subject actually uses drugs. That is, we're finding the probability of positive test result given subject uses drugs. All right. So our intuitive approach, we want to find the positive test result given the subject uses drugs. So we're going to look at when the subject uses drugs has already happened. We want the probability now that there's also a positive test result. So looking at this, we have 50 subjects who are using drugs, right? And we see them in our first row of our table, 45 plus 5, that's our 50 subjects using drugs. And then we look and we see how many had positive test results. Well, we see that in the top left-hand corner, 45 of them have positive test results. So our probability is 45 divided by 50, which is 0.900. So that's our conditional probability using that intuitive approach. So let's take a look at the formal approach instead. The formal approach says that we need to find the probability of A and B and the probability of A and do some division. So the probability of A and B is 45 out of 555. That's the probability that subjects used drugs and had a positive test result. That's 45 people out of the 555 total subjects. And then we're going to divide that by the probability of A. In this case, A is the subject uses drugs. So we're going to find the probability that the subject uses drugs. So of our 555 people, or subjects, we have 50 using drugs. So that probability is 50 divided by 555. So we're going to be dividing 45 divided by 555 divided by the quantity 50 divided by 555. And when we do that, we get 0.900. We get to the same place with both our intuitive approach and our more formal approach. Now, it's really important that we notice that when we use the intuitive approach and the formal approach, we ended up the same place. And the intuitive approach was a lot less cluttered looking. It wasn't those double fractions. When the intuitive approach works, use it. All right. Sometimes you will need the formal approach depending on the information you've been given. But with a table like this, there's no reason not to use the intuitive approach and save yourself the more likely calculation errors that will occur with those double the fraction of a fraction. All right. So now let's take a look at problem B. So problem B wants us to find if one of the 555 test subjects is randomly selected, we're going to find the probability that the subject actually uses drugs given that he or she has a positive test result. So that is, we're finding probability of subject uses drugs given positive test result. So in the first problem, we were using that first row of information, and in this one, we'll be using the first column of information. All right, so keep that 45 and 25 in your mind. So here we have 70 subjects total. That's the 70 subjects who had a positive test result. And we want to find the probability that the subject uses drugs given the positive test result. Well, 45 people used drugs and had a positive test result, and 70 people total had a positive test result. So using our intuitive approach, we get 45 divided by 70, or 0.643. So interpreting both of these results together, with our first result, we had a probability of a positive test result given that the subject uses drugs of 0.900. This indicates that a subject who uses drugs is fairly likely to have a positive test result. Now, with our second result, the probability that a subject uses drugs given a positive test result is 0.643, which indicates that for a subject who gets a positive test result, it's likely, but not super likely, that the subject actually uses drugs. Now, it's important to notice that the probability of a positive test result given that the subject uses drugs is not equal to the probability that the subject uses drugs given a positive test result. This is a common mistake for people to make, thinking that those two things must be equal. This is called the confusion of the inverse. So getting these things backwards or incorrectly thinking that you can replace one with the other because they must be equal, it's a common mistake called confusion of the inverse. Don't make that mistake. Right. So here's maybe even a more straightforward idea to help you keep confusion of the inverse in your mind. So we're going to consider two events. D stands for it's dark outdoors, and M stands for it is midnight. Now, we're not going to be dealing with the Arctic Circle or Antarctic Circle, so we're not going to be dealing with the extreme poles of the globe, but we're going to be dealing with life as most of us experience it, where it's dark at midnight. So the probability that it's dark, given that it's midnight, is 1. Right? So it's certain to be dark, given that it's midnight. However, the probability that it's midnight, given that it's dark, is pretty much 0. All right? Because exactly midnight is a very short period of time that you can't even really measure. We can be seconds before, seconds after, nanoseconds before, nanoseconds after, right? So this probability is pretty much 0, that it is exactly midnight when it's dark out. So very clearly here, the probability that it's dark, given that it's midnight, is not equal to the probability that it's midnight, given that it's dark. All right, our final topic, Bayes' theorem. So conditional probability, we use this thing called Bayes' theorem to help us out sometimes when we want to know something about one conditional probability and we know something about another conditional or the other conditional probability, or we might want to know something like as we obtain more information, our probability stuff changes. So this is Bayes' theorem, very hand-wavy, all right? If you're looking to know more about Bayes' theorem, you're going to have to look beyond this course for that. But we're going to look at an example of how we might be able to extend our knowledge a little bit. So we're going to assume that cancer has a 1% prevalence rate, meaning that 1% of the population has cancer. Denoting the event of having cancer as capital C, we have the probability of cancer is 0.01 for a subject randomly selected from the population. Fair enough, right? So this result's included with the following performance characteristics of a test for cancer. Right, so we have this probability of cancer is 0.01, and now we have a test for cancer that we're adding to the mix. So we know about this test that the false positive rate is 10%. That is, the probability of a positive test result given that cancer is not present is 0.1. We also know that this test has a true positive rate of 80%. That is, the probability of a positive test result given that cancer is present is 0.8. So now that we have this test introduced to us, we want to find the probability that a member of our population has cancer given that they have a positive test result. All right. So we can make up this hypothetical breakdown of our population given the information that we have. So let's break through how do we get all of these numbers in here. Well, we chose 1,000 subjects because the numbers come out really nice this way. And whenever you're starting to get decimals of people, you can kind of up it by a factor of 10, and that'll help cancel out those decimal places so you get to deal in whole numbers of subjects, as subjects actually are in real life. So 1,000 subjects is chosen so that we don't have to deal in decimal subjects. But if you choose the wrong thing to begin with, you'll have decimal subjects, and you can multiply all of your numbers by 10 or 100 and move those decimal places so you end up with whole numbers of subjects. So with a 1% prevalence rate, 1% of 1,000 is 10 of the subjects are expected to have cancer. So in my cancer row, my total number of subjects needs to be 10. That's where that blue highlighted number 10 came from. If 10 of my subjects have cancer, that means 990 of them do not have cancer. So that's where the blue highlighted 990 came from. If we total 990 plus 10, we get our 1,000 subjects. So now we're going to talk about how we get these numbers inside of our table. So looking at the 990 subjects without cancer, 10% are going to get positive test results. That's that 10% false positive. So 10% of the 990 cancer-free subjects is 99 subjects. So 99 of our subjects will get a false positive. Now, if 99 of those 990 subjects get a false positive, that means that 891 of them will get a negative, which is a true negative. So 99 plus 891 is 990. So that's how my entire bottom row has been constructed now. Now for the top row, we know that the true positive rate is 80%. The test results are positive for 80% of patients with cancer. So 80% of our 10 subjects should return a true positive. So 80% of 10 is 8. So 8 people will receive a true positive. And now, if 8 of the 10 receive a true positive, that leaves 2 of them to receive a negative test result, even though they do have cancer, giving us a false negative of 2. So that's how my entire table is constructed using that added information about a test now. So now let's find what we were looking for. We're looking to find the probability that a subject has cancer given a positive test result. Well, positive test results show in the left column. So my positive test results, the total number of people receiving a positive test result are 107, and 8 of them actually have cancer. So this probability is 8 divided by 107, which is 0.0748. So interpreting this, for the data that was given originally, a randomly selected subject has 1% chance of cancer. But if we introduce this test to the mix, for a randomly selected subject given a test with a positive result, the chance of cancer increases to 7.48%. Now this increase looks good. It's helping us identify this. However, both of those values are still fairly low. So a positive test result should not be devastating news for anyone because there's still a good chance that the test was wrong. So we have a couple of ideas that have kind of evolved through this. The first is a prior probability. A prior probability is an initial probability value that's originally obtained before any additional information is obtained. A posterior probability is a probability value that has been revised using the additional information that's later obtained. So in my last example, the probability of cancer being 0.01, that was my prior probability. And my revised probability of 0.07848 of the probability of cancer given a positive test result is a posterior probability because it used that additional information of a positive test result.